Log on, tune in, find out. Another good idea from Cambridge.
It's great to see so many people here, but of course not at all surprising given that we've got Cedric here. Cedric obviously needs no introduction. We give to you our warmest congratulations on your Fields Medal. It's just fantastic that the topic is so close, in fact central to the program on differential equations and kinetic theories that's going on at the Newton Institute at this very moment. I was very pleased to see Cedric and very sorry to see he's taken his split off his wrist, and I don't know whether he's got repetitive strain injury from answering all the email congratulations or from shaking hands with people. Enough from me, shaking hands. Cedric, over to you, and thank you very much. Cedric.
Thank you. Thank you, David. Everybody hear me clear? Okay. So, as David said, his talk is about some of the central principles for the conference program about kinetic theory going on currently at the Newton Institute. And we'll explore here some of the foundational ideas of this kinetic theory and examine their impact on mathematics, not just physics, but also mathematics. This will be a talk that is for broad audience. For experts, it will appear like very simple. I hope for everybody will be understandable, at least in large part, and don't hesitate to interrupt by questions. So here is Boltzmann that you see here. How does this? Yes, this is Boltzmann. And the title of the talk, yes, is Entropy and H theorem, mathematical legacy of Ludwig Boltzmann. So let us start with what I will call in a slightly provocative way, cutting-edge physics at the end of the 19th century. So take a classical gas, no relativity, no quantum effects, nothing, just the classical gas, and interested in the long-time behavior of this gas. What would be a mathematical model for this? Well, you take small hard balls, say a large number, maybe 10 to the 20, maybe this is the number of atoms you have in your box, and they bounce against each other, like a big billiard game. So the gas evolves according to the Newton equations. Okay, I put here founding father here, no, for Newton Institute. So it's good to start with Newton. This is the picture of what it is like. So at each time, you have the particles, they have certain positions and velocities. So the arrows here indicate the velocities. You see here two particles that collide when time evolves. After the collision, you update the velocities according to the laws of the billiard, the usual laws of reflection. So this is your big Newton billiard. And the problem with it is that it's so big, say 10 to the 20 balls. What can you say that would be interesting, intelligent about it? So Maxwell and Boltzmann, at the end of the 1860s, so this is Maxwell, this is young Boltzmann, this is old Boltzmann. They make this very daring prediction at the time that the distribution function of the gas should be asymptotically Gaussian. That is, if you are interested in the statistical repartition, statistical distribution of positions and velocity at a time t which is very large, it should be like Gaussian. This is the usual Gauss shape, exponential minus v square. There is a constant here in front, and there is here another constant that should be interpreted as a temperature. If the temperature is low, the Gaussian would be very peaked. If the temperature is high, the Gaussian would be very spread. And what they say is, okay, the velocity, if you pick at random, say, a ball in your gas, and you measure the velocity, this should be distributed like a Gaussian, the curve of velocities. And this should be independent of the position. You see that here in this formula, there is no x. There is just v that is here that stands for velocity. I will come back to this formalism of statistical distributions of position and velocity. So why on earth would you get this Gaussian out of this big Newton billiard of 10 to the 20 particles in large time? This was based on 4 major conceptual advances going through a decade around mid-60s to mid-70s in the 19th century. and which is kind of small scientific revolution in a sense. First, a major modeling advance, which was the Boltzmann equation. This is a new model for classical mechanics, for some problems classical mechanics, in this case dilute gases. Now, a major mathematical advance is the notion of statistical entropy. Entropy at the time was already a notion that was being developed in the context of thermodynamics. But now with the statistical meaning, it acquires a whole new dimension. Major physical advance, theoretical physical advance here at the same time is the notion of macroscopic irreversibility compatible with the microscopic reversibility of Newton. And the fourth advance is a major partial differential advance, partial differential equation advance, a qualitative functional study of some partial differential equations. I will describe these four advances, and this will take most of the talk. And while doing this, this will be the occasion to take a journey around some scientific problems that have been around for more than 100 years, most of which are still not solved or only partially solved. Boltzmann equation is a model for rarefied gases, first introduced by Maxwell in 1865, then developed by Boltzmann a few years later. Here are some pictures of books by the late Carlo Cerciniani, who did a lot to popularize the theory of the Boltzmann equation and make it progress. This is a kinetic model, so the unknown in the Boltzmann equation is a function f of txv, which you can think of as a probability distribution, for instance. It gives you the density of particles in the position velocity space at time t. Roughly speaking, say, if you want to know how many particles lie in a fraction of space that is modeled by dx dv, so dx is the dx in position and dv in velocity, then you integrate f of txv over this small volume dx dv. Another way to say it, if you think that f is normalized mass to 1, is if I pick a particle at random at time t, and I measure its position and its velocity, it will be, roughly speaking, distributed according to f of xv, the distribution of particles. So it's a statistical description of the gas in which you don't try to follow all the particles, all the velocities and position of these 10 to the 20 particles, which would be a crazy thing to do. So Boltzmann equation. This is the Boltzmann equation. To simplify things, I will not write boundary conditions. And the unknown, as I said, is a time-dependent distribution function. So f depends on time, position, and velocity. F is non-negative. And here it is. Just this in blue is the Boltzmann equation, df dt. So it's in dimension 3. Sum of vi df dxi is equal to q of ff. Q of ff is this complicated integral operator devised by Boltzmann. Let me explain a little bit the features of this equation. First part here, which we have on the left-hand side of the equation, is differential part. F depends on x and v. X has three components for the 3 dimensions on space. These vi here are the 3 components of velocity. So here, what we are here is the scalar product of the velocity by the gradient of f with respect to the x variable. This operator on the left-hand side is here only to say that particles, they like to go in straight lines. This we know since Galileo. If you don't have interaction between particles, they will just go in straight lines, and that's all. Inertia principle, if you want. Now, Boltzmann adds another term. Maxwell and Boltzmann add this quadratic term on the right-hand side, which models the effect of collisions. From time to time, 2 particles will collide, and this will have an effect on the distribution function. Because of this collision, some velocities will become less represented, some velocities will become more represented, etc. And how much should we subtract or add to the distribution function is here described by this operator. What is in this operator? First of all, there are 2, it is integral over all possible velocities v star and over all possible parameters sigma on a sphere. Here I'm still in 3 dimensions, so here this is the 3 sphere, unit sphere in R3. And here appear in this equation v and v star, which are the particles, if you want, of the velocities of two particles which will collide, and v prime star, the velocities of two particles, the same two particles after collision. If you think about it, v and v star, this is 3 components and 3 components, so 6. Here also 6 components. When two particles collide, this is an elastic billiard. So you have conservation of momentum. This is 3 conservation laws. And conservation of energy, this is 1. So this is 4 out of 6. Remain 2 degrees of freedom. And these are taken into account by this parameter sigma. And once you fix the parameter sigma, you can represent the velocities after collision in terms of the velocities before collision. It could be the reverse, because these laws of the billiard are reversible. If you look the movie of the billiard forward or backward, it is the same. So you can also say that v prime star, the velocity is before collision, and dv star, the velocity is after collision. Next, in this equation, t and x in the right-hand side appear only as parameters. It was not so for the left-hand side. Here we would add the derivative of f with respect to x. This is normal because as particles travel, this changes the density of particles over space as they travel in straight lines. But on the right-hand side, the idea is that collisions occur on a scale which is so much smaller that you don't see the difference between the positions, the change of positions caused by the shock. Shock is something that is kind of instantaneous and just modifies the velocities, as in my picture here, remember? So shock is something going from here to here. No change in the position distribution, but changing in the velocity distribution. So t and x here are the same in these various occurrences of f. And next thing you notice here is that f appears in the form of a product, like a tensor product. F of v prime times f of v prime star. F of v times f of v star. This corresponds to a notion of molecular chaos. It's the idea that if you take two particles that do not know each other, that have nothing particular, they will not be correlated. You have your gas, I take one particle and then another particle. A measurement on the velocity of the first particle should not give me any information on the velocity of the second particle. That is the idea, if they are both taken at the same position. Molecular chaos, no correlation between particles. And it's like in probability theory, when you have probability of two random variables that are uncorrelated, the joint distribution function is just the tensor product. So here also you take tensor product of f by itself. However, this is very tricky from conceptual point of view, because whenever particles collide, correlations form. The two particles did not know each other, maybe before the collision, but after the collision, they know each other, they have influenced each other. And then you cannot say that they are uncorrelated. So correlations should form. Then this molecular chaos assumption has to be replaced by one-sided molecular chaos. No correlations on pre-collisional configurations. Before you encounter another particle, you don't know anything about it. However, there should be correlations on post-collisional configurations. And this should be preserved in time, although correlations continuously form. So correlations are created by collisions, but they are forgotten and forgotten. This has triggered a lot of discussions. This, from an analyst's perspective, is very frightening. We want to do estimates on something which are probability distributions. We cannot say that they are just tensor products in the usual sense, because we want to be able to detect pre-collisional configuration, which is a rare event, and we want to see that there is no correlations when the two particles are just about to collide. So we'd like to have some thing like an everywhere assumption, but you cannot say it everywhere, because just after collision it should be correlated. So somewhere in between almost everywhere and everywhere, it's a bit, okay, frightening. We have no good answer for the moment to this. And is it a valid approximation? Then came 100 years of controversy involving physicists and mathematicians, and physicists went, okay, this is an approximation, it's not really true, we should derive it, okay, it's phenomenological, or who knows. Then arrived mathematical theorem. Probably the most important single most important theorem in the theory remains the Lansford theorem from 1973. Lansford rigorously derives the Boltzmann equation from Newtonian mechanics of n-hard spheres of radius r in the scaling where nr squared goes to 1. So n is very, very large, r is very, very small, and you take the limit, n goes to infinity, r goes to 0, and r squared goes to 1. In this limit, you recover the Boltzmann equation. For distributions with Gaussian velocity decay, so there are some technical assumptions about the velocity profile of your data, which is okay. The time interval of Lansford is short but macroscopic. This is a time such that maybe 1/6 of the particles had the time to collide. It doesn't seem much. Most of the particles in the Lansford theorem did not yet collide once. However, this is conceptually very important, and this was the first result showing that you could really get this Boltzmann equation out of the Newton equation. Later, Illner and Pulviarenti improved this to rare cloud in R3 for all times. If you have a gas with very small mass, then you can establish Boltzmann equation from Newton dynamics. There has been recent work also on the quantum case. Important as it is, the Lansford theorem leaves many open issues. No idea about large data, which means large time or no constraint on the mass. No idea about what happens in a box. I mean, if you do your experiment in a lab, your gas is inside a box. Lansford theorem is in the whole space. What about long-range interactions, which are very important too? No idea. The proof is based on representation of trajectories, which is very cumbersome, and we would like to do without this. And most importantly, maybe, the Boltzmann equation should be based on this subtle one-sided chaos that there are no correlations between particles which are about to collide. But the Lansford theorem tells you nothing about this propagation of one-sided chaos. So the mathematical reason why it works in the
point did Lansford lose reversibility? Because he started with reversible dynamics.
Of course. This is all about the initial. I'll come back to it at some point, but it's all about the initial datum. When you prepare, suppose I prepare my gas, I prepare it, and the initial datum I will prepare is something special, say no correlation at initial time, not at all. I take particles at random. This is very likely because in general, if you take a gas at random, say, there will essentially be no correlations. Then from that time on, there will be 2 arrows of time from this special initial datum. One forward in time, one backward in time. And there will be 1 arrow of time like this, 1 arrow of time like this. And you should have one-sided chaos like this and one-sided chaos like this. In each direction of time, you preserve, you keep creating and destroying correlations. So you keep reversibility. Just there is a particular time, and from that particular time on, there are two directions. Did I answer a question? Okay.
So you mean he couldn't verify his conditions at time not equal to 0?
That is exactly true. His proof is based on representing the solution as a perturbation series in which everything is expressed in terms of the initial datum. And then you use the assumption on the initial datum, which are extremely strong, to prove the result. And you identify the limit. It's a crazy way to do. It's like but it works. It's the only method so far that works. It's like to identify some evolution, you write the exponential in terms of the series, try to identify each term of the series. And the exponential T, L, x0 is all expressed in terms of x0, the initial datum, and then use the assumption of f0. But you don't see that something is propagated. So this is maybe the main problem. We are not really satisfied with this. With this proof, we feel okay. We still don't understand. Now, anyway, at least you have now this connection between Newton mechanics and Boltzmann equation. You'd like to know more about qualitative properties. Fundamental properties of Newtonian mechanics is the preservation of volume in configuration space. This is Hamiltonian system. You even have more, but at least you have the Liouville theorem that the volume is preserved for the Newtonian mechanics. Here, as n goes to infinity, we go to infinite dimensional system. What does the volume mean, and what do we obtain with this? Is there something playing the role of volume in the Boltzmann equation that would have some interesting property? What can be said so about the volume? This leads us to our second point. which is the entropy, and the Boltzmann's H functional. So Boltzmann calls H, okay, for some reason he had a choice of sign which is not so good, but let's keep with his choice of sign. So S is the really physically meaningful quantity, is the negative of the H functional of Boltzmann, and this H functional is integral of f log f. And you integrate over the phase space in velocity and position, all around your box with all positions and all velocities. And Boltzmann identifies S with the entropy of the gas. And he proves that S can only increase in time for the Boltzmann equation. Moreover, the increase is strict unless the gas is in a very special state that is hydrodynamical. So, before I comment more, first you see this is an instance of the second law of thermodynamics. As we learn in the elementary thermodynamics course, entropy increases. If you have a system that is isolated, etc., entropy goes up. Here it's the same. Entropy of the gas goes up. However, this is a monster conceptual progress, which Boltzmann was extremely proud of, that you prove, okay, it's not completely rigorous by mathematician standard, but not so far from. And the proof is beautiful, by the way. So Boltzmann proves that the entropy increases in time. It's not a law any longer, it's a theorem. Law is something you don't discuss, you accept without questioning. Now, theorem is something you understand, a reason for. What is the content of this H functional, or this entropy, so which is the same as the entropy up to a sign? This is Shannon, father of the theory of information that now is everywhere underlying our cell phones and laptops and whatever. The same H functional that Boltzmann used appears in the Shannon theory of information. Here is a quote which I like by Shannon, giving some light on the role of mathematicians in this terminology. Shannon said, "I thought of calling this quantity information, but the word was overly used, so I decided to call it uncertainty." Okay, it is strange when you read this. Why information and uncertainty seem to be opposite of each other? In fact, it's a question of point of view. Information is about uncertainty. I mean, information is what you gain when you decipher some message. The more it is uncertain at the beginning, the more information you will get. If you know in advance what will occur, you don't get any information. Usually the case, as I tell my students, when you have political statements by political men, depending on the political color of the person, you know in advance what he will say. Then no uncertainty in advance means no information. You get no information from the okay. Now Shannon continues. When I discussed it with John von Neumann, he had a better idea. You should call it entropy for two reasons. In first place, your uncertainty has been used in statistical mechanics under that name, so it already has a name. So that's a good reason. Second place, and more important, no one knows what entropy really is. So in a debate, you will always have the advantage. It's good. Okay. So those of you who never understood entropy now understand why. Now, in spite of this curse by von Neumann, let us try to understand what is entropy. So let's call this Shannon-Boltzmann entropy. S equals minus integral of f log f. It quantifies how much information there is in a random signal or language. You imagine that you have a set of possible outcomes, and this is described by some probability measure nu. Nu has a density with respect to your reference probability measure mu. Mu may be like a volume measure if you are in the context of statistical mechanics of Hamiltonian systems, or some other natural measure. And entropy, so is this. So information is this integral of rho log rho, integral of f log f, where f or rho is the density. So the meaning is exactly the following. Entropy measures the volume of microstates, that is microscopical states, associated to some degree of accuracy in macroscopic observables to a given macroscopic configuration. Macroscopic configuration is what you can observe by making some experiment. Is the observable distribution function. Maybe you can measure the pressure, you can measure some statistical quantities. More generally, what you can measure maybe is this density f of txv that tells you the statistical repartition of velocities. You cannot measure the velocities individually, only statistical distribution you can. Now, for any macroscopic configuration that you can measure, there is a large amount of microscopic possibilities, microstates, which is the way all velocities and positions are arranged. This very large volume of configurations is what the entropy measures. So entropy tells you what is the amount of uncertainty that is left on the microscopic structure of what you're observing after the observation. How exceptional, in particular, is the observed configuration? If it is very rare, it will be easy to reconstruct the microscopic configuration from the macroscopic observation. The most critical example would be like every particles would be concentrated in one given point, like kind of Big Bang or whatever. Then just from the observation outside, you know the microscopic configuration. Conversely, if it's all spread, then it's very difficult to guess something from the macroscopic observation. A note that is good to keep in mind is the entropy is an entropic concept in the sense that it depends on the observation, here entropic in the sense of man. Depending on what the observation that you can make, it will change your entropy. In some sense, if you are godlike and you know everything in the world, there is no entropy. Now, here is the Boltzmann formula. S equals K log W. K is a constant. W is this microstate, the set of microstates, the volume of microstate story. So S is K times the log of possible configurations. This is a very nice formula that you can see on the grave of Boltzmann. Maybe you don't see it so well here. This is in Central Friedhof in Vienna. Okay, here is story behind the picture. Oh, so my friends already heard me telling it a lot, but not other people. So imagine I arrive in this cemetery, and it's very large. You can spend your whole day in this Central Friedhof cemetery. And then there is no map or whatever, so it was a bit late. So I see some tourists there sitting on a bench, and I ask, you know where I can find a map or some information about the cemetery? No, there is no information. Who are you looking for? I say, Boltzmann. And the guy looks at me in the eyes and says, S equals K log W. And he took the picture of me with the formula. So you see, it's important. But now, it strikes the mind. But now you can say, okay, now my friend, you're cheating us because you gave us two formulas. One object with two different definitions, K log W on one hand, minus integral F log F on the other hand. How can we reconcile this? This is the genius strike of Boltzmann. That this is a general formula, S is K log W, which in the case of kinetic theory has this more computable formula, minus integral F log F. And here is how the computation goes. We'll go through discretization of phase space. So positions and velocities, let us assume this is in a box, like we live in a discrete world, just for the sake of the explanations. And we have a large number of particles, n, say n is 10 to the 20, that we have to put in k boxes, which are like the states in physical space, positions, and velocities. Now, what we can observe is a statistical distribution. Let us give ourselves such a distribution. F1, etc., Fk will be the proportion of particles in box 1, Fk, the proportion of particles in box k. Obviously, the sum of these frequencies should be 1, and we'll ask them to be rational so that it's possible that they are compatible with some way to arrange these n particles in the boxes. Then let's call capital Nj the number of particles in box number j, and given f, the admissible configurations are those such that Nj divided by n, so the frequency that is observed corresponds to the frequency that we were guessing in advance. So this is what we measure, and we want to see what are the number of configurations which are compatible with this. So, example, if I know that all particles are in box number 3, there is just one possibility. If I, yes?
Because velocity is in the definition.
Yes, exactly. If I know that I have 8 particles, 3/4 are in box number 3, 1/4 in box number 5, then it's simple exercise that number of such configuration is 8 factorial divided by 6 factorial, 2 factorial, simple combinatorial exercise. More generally, the formula would be n factorial divided by the product of factorials of the numbers of particles in each box. Then, we're interested in the limits, in continuum limit where there are many, many such particles, so we'll take n to infinity. So, this is the same as already said. As n goes to infinity, using the formula before and Stirling approximation, it's simple exercise to show that up to non-essential constant, the number, the cardinality of the configurations that are admissible grows like exponential minus n sum of fj log fj. And in particular, if you take the logarithm, divide by n, look in very large n, this is an approximation of minus sum of fj log fj. So here, on the left-hand side, you have the first definition, k log w, and on the right-hand side, the other definition, minus integral of f log f. So that's the link. Of course, this is a simple model with discrete, just put particles in boxes. So how do we do a thing that is more general? The mathematical translation of the Boltzmann intuition in general is called the Sanov theorem. It's part of the theory of large deviations in which you're interested in probability of hitting rare events. And here is how I will present it. So take x1, x2, etc., microscopic random variables, independent of each other, all with the same law that is mu, distribution probability of x1 and x2, etc. From a number of observations, you cook up the empirical measure, which is the average of Dirac masses, Dirac at point x1, Dirac at point x2, etc. This is a measure which contains all the information about the cloud of particles, regardless of their labeling. What measure will we observe now? Intuitively, this measure should be a good approximation of mu. This is usual theorem of statistics. If you have a signal that is distributed according to, say, a Gaussian, and you draw a large number of samples, you put a small dot wherever you have something, and you look at concentration of dots, it should be approximately Gaussian. And then you ask, how about the probability that it deviates from mu? This is what large deviation theory is about. Probability of the rare event that the empirical measure is approximately nu, with nu not equal to mu, not necessarily. And this probability will be exponentially small with n, and the coefficient that you have here in front of n is exactly the information, the Boltzmann information. So it gives you the how much the way that how much it is likely that you hit the measure nu by taking samples with the low mu and looking at the random measure, which is the empirical measure. So this is a fuzzy writing, of course. What does it mean? Probability on the space of probabilities, etc. Rigorous writing is not so fun. And involves 3 limits, and you cannot do without it. So let's try to understand. Here I take observations, x1, etc., xn, and I look at an observable. Observable is a function, maybe the first coordinate, or maybe the square of the velocity, the kinetic velocity or something, some function valued in r. I will take the average of this function evaluated at the points xn, x1, etc., xn, and I will compare this to the average, theoretical average that I would have obtained from the this probability distribution nu. And so each phi j is like an experiment. One experiment is about measuring kinetic energy, one experiment is about measuring one component, etc. And this, I will see if this agrees up to a certain precision, epsilon. And I will do this for a number of experiments, so each j corresponds to one experiment with values in r. And I will look the probability that the agreement is good, take the logarithm, divide by 1 over n. Then I take the limit as first as the number of observations goes to infinity, or number of particles. then the accuracy goes to 0, very small accuracy, and then the number of observables of experiments goes to infinity. If you do the limit in the wrong order, it doesn't work. So after these definitions, let me make the point that entropy is a universal context. It's not only about kinetic theory, it is much more general. And here are some examples I will give. First, the lax entropy condition is used in compressible fluid mechanics to select physically relevant shocks. Shock is like discontinuity in certain variables that occur spontaneously in fluid mechanics sometimes. And when you have a shock, you have an ambiguity. The equation is not sufficient to let you go forward, and you should select physically relevant solutions. Lack understood that the physical requirement that the entropy should always increase in a shock, that this information should be lost and never created. Okay, usually it's stated with the other way around, entropy should decrease, but that is because Lax uses convex entropies while entropy should be concave. Here is another example that will be more exotic in the sense that will come from completely different world, not classical physics at all, which is the Voiculescu classification of type 2-1 factors that I will evoke very briefly. I am not competent on this issue, but I will point out the relation with the Boltzmann entropy. Let's do some very quick reminders about von Neumann algebras. Initially, this was motivated by quantum mechanics or group representation theory. Then, in a way, it became an area on its own. You start from a Hilbert space, okay, infinite-dimensional separable Hilbert space. You look at bounded operators on H. You equip this with operator norm. By definition, a von Neumann algebra would be a subalgebra of B of H, containing the identity, stable by passing to the adjoint, and closed for the weak topology. And then you're interested in classifying these objects. This is still an active topic with some famous unsolved basic problems. And there are some classifications like type 1, type 2, type 3 with subclasses and so on. And among them, there are some von Neumann algebras called type 2-1 factors. Factor is an infinite-dimensional von Neumann algebra with trivial center. So if you commute with everything, you are identity or multiple. And you see that it is type 2-1 when it has a tracial state, which is a linear form tau, such that it is non-negative. Whenever you take A, trace of A star A is non-negative. It is normalized to 1, so tau of identity is equal to 1, and it has the tracial property tau of AB equal tau of BA. These properties are reminiscent of a probability measure, and for that reason, A tau is called non-commutative probability space when this occurs. Now, sometimes these spaces may arise as macroscopic limits of microscopic objects, which in this case are large random matrices. So take x1, etc., xn, large matrices, random, so you put probability measure on the distribution of coefficients. And whenever you take a polynomial, this will be a non-commutative polynomial P. You look at the trace of P of x1, etc., xn, expected value of this guy, divide by n and take the limit as n goes to infinity. Under certain assumptions, this will define a tracial state tau. In the same way as sometimes from microscopic dynamics, you get some macroscopic equation as Boltzmann equation, by the way. So this was the idea of Voiculescu. Let's try to find a new invariant for some of these 2-1 von Neumann algebras and think of a collection, for instance, a collection of self-adjoint operators A1, etc., An, as the observable limit of a family of microscopic systems that would be large matrices, and copy the definition of Boltzmann. So if I am given A1, etc., An, these are like macroscopic state, what I can observe. I look at the set of all matrices, this will be like microscopic configurations, very large, n times n Hermitian matrices, such that for any polynomial plays the role of an observable before. It's like an experiment that you perform. When you take a polynomial and you look at the trace, both coincide, the macroscopic and the microscopic, up to an error epsilon. And this would be true for all polynomials of degree less than k. In this case, you have a way to order all possible observables by just the degree. And then, as before, you take 1 over k, so this is k log w, and you take the limit as number of particles goes to infinity, accuracy of experiment goes to 0, number of experiment goes to infinity. And you define something that is the Voiculescu entropy, and that was useful to him in the solution of several long-standing problems in operator theory. As you see, it is again the Boltzmann formula, adapted to this context. Here is another example now. Let's be back to something that is more classical maybe, but still very interesting. So central limit theorem we all know. You take identically distributed independent real random variables, for instance, x1, x2, etc., xn, with finite second order moment, and centered, so mean value is equal to 0. Then when I look at an average over n experiments and divide it by square root of n, this converges to a Gaussian random variable. If I divide by n, this goes to 0. This is law of large numbers. But if I divide by square root of n, this will become a Gaussian random variable in the limit. This we know and usually is proven by Fourier analysis. There are other proofs also based on Taylor formula. Now in 2004, Boltzmann and Naur found a very nice interpretation which should be the way you would explain central limit theorem to Boltzmann if you wanted. And the way is that under this process there is an irreversible loss of information in the sense of Boltzmann. If you look at the entropy of this random variable, which is like dynamical problem in n, this will always increase with n. It's not only easy to prove. Then you will increase, and in the end you converge to the state of maximum entropy. And maximum entropy, if you fix under this scaling, if you fix the first and second moment, is a Gaussian. So this is a new interpretation of the role of the Gaussian in central limit theorem. Back to Boltzmann now. Let's talk about this H theorem. And this will be my next point about the impact on the Boltzmann discovery on the analysis, qualitative analysis of the partial differential equation, which is in case the Boltzmann equation. So what Boltzmann does is to compute the rate of variation of entropy along the Boltzmann equation. I told you the law of H theorem is a theorem, it's not a law. So you show that the entropy increases. In fact, Boltzmann computes the time derivative of the entropy. And this is the formula. Okay, is an integral over 2 plus 3 plus 3 plus 3 variables. It's a lot. But whatever, you see it has this formula, this structure like A minus B multiplied by log of A over B. A minus B times log A over B is always non-negative. This is just because logarithm is increasing. So obviously this thing is non-negative. Moreover, Boltzmann shows that this is 0 only if f has a special form, which is that in the velocity variable it is a Gaussian. And it is a Gaussian that is centered around some velocity u that may depend on x. How much it is peak depends on some parameter t, which is like a temperature which may depend on x, and in front there is a coefficient which is like a density which may depend on x too. This depends on much less parameters than the whole distribution f. It depends just on a function rho, a function u, a function t, density, velocity, temperature. These are the basic unknowns, the basic fields in classical hydrodynamic theory. And the main equations like Navier-Stokes or Euler equation are expressed in these terms. So this is the bridge established by Boltzmann between the kinetic description, if you are interested in statistical distribution of positions and velocity, and the hydrodynamic description in which you are interested in density, temperature, mean velocity at each point. So entropy goes up. Entropy increases, and then what about?
Say only you mean for any probability density for which you have this formula.
Yes.
Not under any additional restriction.
Okay. So there are some. They are very weak. I don't know what is the best, what is the optimal result, but they are extremely weak assumptions. Even measurable. Yes, this is our carried work. Okay. Now, there is another question about reversibility related to the question that was there. Entropy goes up. However, Newtonian mechanics is reversible. This was the start of many controversies. Some people question the Boltzmann arguments. Okay, there was this computation. Computation gives that it's non-negative, and because it's zero if and only if you have this, then necessarily it has to increase strictly, except if you start from a state that is not hydrodynamical. Then they say, okay, but how is that possible? Because the Newtonian mechanics is reversible. You see that Poincaré, unfortunately, took part in this discussion in a way that should be forgotten. So here is an experiment that was a thought experiment. Like, okay, first take your box, divide it in two. You put a gas in the right compartment, nothing here, and you let free. Okay. What will happen? We all know. The gas will go and invade the whole box. However, there is the Poincaré recurrence theorem, which is a true theorem, I mean you establish it, that tell you that if you wait long enough, then all the particles will be back at their original positions, or almost, arbitrarily close to. Then if you measure the entropy, how is it possible? It should be the same at this state than it was at this state, or kind of. But that is not plausible explanation. And has Boltzmann got the point? If you, first we know this does not occur. You can make the experiment and you wait long and long and long enough. They will never go back to their compartment. In fact, if you try to compute recurrence time, you need times that are much, much, much larger than the age of the universe. This will simply not occur on a time scale that is reasonable. That is on the macroscopic time scale. Second objection was this Loschmidt paradox. You wait until time t, then you reverse all velocities. You saw the formula for the entropy. Integral of f log f, if you reverse the velocities, this will not change. Then you start again. Then this will be again the Boltzmann equation, and entropy will increase again. However, by microscopic reversibility, you will be back to the initial configuration. If I reverse velocities, you will run the movie backward and arrive at the initial configuration because the Newton equations are reversible. So then you would be back to initial configuration and initial entropy. And you are in trouble. Boltzmann here had an interesting answer. Go and reverse them. Of course, you cannot do it. And again, there is something to it. I mean, when you act on the system, you act macroscopically. You're not like God acting that says, okay, let the velocities be reversed. You cannot do this because we are macroscopic beings and we can only act on the gas through macroscopic experiments. And also this shows us the subtleties of one-sided chaos. Because what happens if we were to say this? Remember one-sided chaos. You start from configuration which is completely chaotic, and then you go forward in time. Just before the collision, it will be no correlation. Just after correlation. Now, if I reverse all the velocity, it will be the contrary. And then the relevant equation will not be Boltzmann equation, but Boltzmann equation for negative times, which occurs with the minus in front of the right-hand side, minus q, and then there is no paradox. You will indeed go back to the initial state if you do this. But the equation has to be changed precisely because you have done something which is not a macroscopic operation. And then you have acted on the configuration space in such a way as to produce a very unlikely initial condition. I mentioned this also in passing. It's subtle, the discussion. There is a notion of macroscopic entropy. There is also the microscopic entropy. The macroscopic entropy is the one I discussed. The microscopic entropy would be the integral of fn log fn, where fn is the distribution of all microscopic velocities. This one is preserved. It's the entropy of somebody who knows everything. This one is preserved. This one increases. When you perform something initially by a macroscopic experiment, usually you prepare yourself in a state of low entropy, unlikely observed state, like put all the gas in one side of the box. However, if you do things with a macroscopic experiment, you will naturally choose things with a very high microscopic entropy because you have no control of the microscopic configuration. And typically, there will be, for instance, no correlation between particles if you prepare this with a macroscopic experiment. So initial entropy is at the same time low and high. It's very high in the sense that it's very high microscopic entropy given the macroscopic state, but the macroscopic state has low macroscopic entropy. Okay, so this is subtle and rich and still up to date. In the debate, Boltzmann was quite appreciated by mathematicians. I show these various quotes. All of us younger mathematicians stood by Boltzmann's side, by Sommerfeld. Or quote by Hilbert, Boltzmann's work on the principles of mechanics suggests the problem of developing mathematically the limiting processes which lead from the atomistic view to the laws of motion of continua. It's part of the sixth problem. Or quote by Mark Katz, Boltzmann summarized most of his work in the two-volume treatise Vorlesungen über Gastheorie. This is one of the greatest books in the history of exact sciences, and the reader is strongly advised to consult it. So, of course, what is nice is that it's not a physicist who says this, but a mathematician. Back to the Boltzmann equation. So once again, as I said, what can we learn at the point of view of the partial differential equation from this H theorem? So far I discussed things about the microscopic meaning, the statistical meaning, some theorems, some problems about arrow of time. But from a point of view of partial differential equation or somebody who wants to prove something about the gas, what do we learn from it? A first remark is that the most important nonlinear models of classical mechanics have not been solved. I mean, be it compressible or incompressible, Euler or Navier-Stokes, that is without or with the viscosity, or the Boltzmann or the Vlasov-Poisson. In all these cases, we still don't have a good mathematical theory that we can say, okay, it's satisfactory, it treats the generality that we want. Crucial importance is to get some qualitative estimates on these equations, and in a way, the Boltzmann's H theorem was the first non-trivial qualitative estimate. The finiteness of the entropy production and of the entropy in particular first prevents clustering. If you have a measure that has finite integral of f log f, it cannot be a Dirac mass. This is trivial. But already this has interesting consequences. From a mathematical point of view, it provides compactness, which was crucial in the first theories of Boltzmann equation, the Archieri theory for homogeneous equation and the Di-Pern-Alliance more general stability theory. And next, the H theorem is the main explanation for the hydrodynamic approximation of Boltzmann equation. Why do you pass from microscopic description that is Boltzmann-like to the equations of hydrodynamics? This is because precisely the H theorem disadvantages all distributions which are not hydrodynamical. These hydrodynamical distributions are the only ones which make the entropy production vanish, and so they are kind of favored in a regime where you have many, many, many collisions, which is the hydrodynamical regime. Another problem where this plays a crucial role is the large time behavior. The state of maximum entropy given the conservation of mass and energy is a Gaussian distribution. And this Gaussian distribution is the only one which prevents entropy from growing further. This is a development of the Boltzmann H theorem. So if we try to guess the behavior of the entropy, we would draw it. This would be something like this. Here I have the entropy of the Gaussian. Entropy grows, so maybe it will approach. And we know that entropy has to grow unless it approaches, it coincides with the distribution of the Gaussian. So this is what we can guess as behavior of the entropy. And if this is true, then f becomes Gaussian as t goes to infinity. And now we are back to the very first slide, or almost, where I explained the prediction by Maxwell and Boltzmann. The distribution function will become Gaussian. See how much there is conceptual content behind. Now, if we try even to prove this last step of the program, this is not so easy. If you want just to prove that a nice solution of the Boltzmann equation approaches the Gaussian equilibrium, this is short, this is easy. Basically, it's the Boltzmann argument. But if you want to get quantitative estimates, that is after a time like 1 hour or whatever, distribution is close to Gaussian up to an error of 1%, this is much more tricky. In this context, time scales are very important. You saw the discussion about the paradoxes. To avoid the paradoxes, we have to keep into account the time scales. And Boltzmann equation will be valid only up to a certain time scale, which is much shorter than the recurrent scale of time scale of Poincaré. So we should be concerned about this. This is a program that is tricky and long, and that lasted for a long time, started with Cercignani, then was pushed by De Villet and Carvalho, and arrived in particular at the conditional convergence theorem by De Villet and myself a few years ago. What does it say? Take a solution of the Boltzmann equation, the appropriate boundary conditions. Assume that f is very regular, uniformly in time. So all moments are finite and all derivatives are bounded, for instance. And assume that f is strictly positive. So you take a very nice solution of Boltzmann equation in which you know that you don't have any analytic problems. Then f will converge to the Gaussian, which is in f infinity state, asymptotic state. And the convergence is fast. It's faster than any inverse polynomial in time.
Is it possible to verify these assumptions?
In certain cases, yes. In other cases, it's wide open. This is, I say, maybe simpler, maybe more difficult than the $1 million problem of Navier-Stokes. But this is
believed to be true.
Then it depends on who you ask. I believe yes. Others believe no. In some cases, you can prove it fortunately. That means the theorem is not void. But the theorem is not. The conceptual importance of the theorem is, at least if you have the regularity, then you have it. Then, of course, I'm simplifying things. I mean, so one can be relaxed. So, besides, this business in PDEs, usually there is critical regularity. When you have a certain regularity, then you have everything. For Boltzmann equation, it's rather low. It's not a question of regularity. It would be a question of integrability. Okay, also the assumption 2, I put it, but I could remove it. If you work using regularity theory, you know that 1 implies 2. Clément Mouot is one of the experts here in the room in this kind of business. And I would say also that this theorem was recently complemented with an exponential rate of convergence for hard spheres model, which is the initial model I described by Gualdani, Michler, and Mouot. Then, also there is something. I have to say I myself was surprised about this. At beginning, in partial differential equations, regularity is so difficult that we tend to believe, okay, if we get the regularity, then we have everything. It would be so nice, and then everything would follow. And it takes time to convince your colleagues that even if you have the regularity, a lot of the work remains to be done. And in this case, even if you have all the regularity, that I mean the complete proof of the theorem goes around 100 pages or so if you add up all the various steps. So this is interesting psychologically for us. There are some areas of mathematics in which there are no such constraints. I mean, sometimes we assume if Riemann hypothesis is true, then blah, blah, blah. Or if this conjecture is true, then blah, blah, blah. But for a PDE person, assume that regularity is true. This is a problem. And then there is a hydrodynamic description, so fluid mechanics. Who are fans of Boltzmann equation like me, one of the beautiful things is that it is a meeting point between the world of statistics and information theory and the world of fluid mechanics. And these worlds come with completely different techniques, and you have to match them when you want to get good results. The matching, putting them together is one key thing. Now, entropy appears. This theorem is based on entropy, and entropy is very rich, and in particular, you can decompose it in a kinetic and a hydrodynamic parts. Entropy will measure, in particular, how close or far you are from being this very special hydrodynamic state. And use a bunch of functional inequalities coming from various fields. So as I said, information theory, quantum field theory, elasticity theory. This was a surprise. This is the part that we like a lot when we work on these on equations. From physical point of view, then you go back to the physicist and say, okay, is there something interesting we learned from physical point of view? One thing that we pointed out after this study was that the existence of oscillations in entropy production. You remember the picture I showed you? This would be the guess of what is the curve of the entropy. In truth, it is not like this. In truth, it is like this. And these are numerical simulations that were made by Philbé on the request of De Villet and myself, because after working on this, we were convinced you would have these oscillations in the entropy production. So look at this. This is like the negative of the entropy in a log plot in time. So it should go down with time. And exponential convergence corresponds to this being rather like a line. Okay? And as you see, it's not a very straightforward thing. And that sometimes it is slowed down, and like this, the decay is slowed, and this is accelerated, and so on. At a time like this is very close to be hydrodynamical, and the decay becomes small. These two curves are what? One corresponds to the global entropy, and the other one corresponds to just the hydrodynamic part of the entropy. Or is it? No, just the kinetic part of the entropy. So when the two curves are very close to each other, this is a state which is the contrary of hydrodynamic, would be spatially homogeneous, in which all the information lies in the velocity distribution and not in the space. When the curves are very far from each other, this is almost hydrodynamic. You see here, the curves are very far. This corresponds to the entropy production slowing down. And here we are very close to be hydrodynamic. And here again, very close to be kinetic, to be homogeneous. Here it's even more frightening in a way. In this example, you start from a situation which is almost hydrodynamic, and after a relatively short time, we are almost homogeneous. It goes exactly at the contrary of the usual idea that has been there for many years, and still is usually believed by physicists, that typically you will first relax to hydrodynamic state, and then the hydrodynamic parameters will homogenize. This thing is just not true if you work in a fixed box. This is related also to more general thing and current research on convergence for non-symmetric degenerate operators. I will not say more about it, but this kind of phenomenon is not just the Boltzmann equation. It occurs in more general equation in which you have some degeneracy. Here, degeneracy would be these hydrodynamic states, because at hydrodynamic states, you don't produce any entropy. It's like degeneracy. Okay, let me, I've been over a bit over time. Let's be very quick and conclude with some other quantitative use of entropy in a priori estimates, and then one final example just after. So, as we know, the entropy was instrumental in the Nash proof of continuity of solutions of linear diffusion equations with non-smooth coefficients. As I learned very recently from Leonard Carlson, it is him who pointed out to Nash the interest of the entropy, and he got it from Kahneman, who was working on Boltzmann equations. So there is a way from Boltzmann to Nash. It is also an entropy formula, although not exactly the same, which allowed Perelman to prove the Poincaré conjecture. I mean, one main core is an a priori estimate in the Perelman proof, which is based on entropy, rather a combination of Fisher and Boltzmann entropy. Entropy is was also used by Varadan and co-workers or students for infinite-dimensional hydrodynamic problems, and then people use it again. This was the subject of my more specialized talk earlier this morning. Entropy is also the basis for the construction of the heat equation in metric measure spaces. How do you do to construct the heat equation in non-smooth setting? This was recently solved by Savaregili, okay, and there is other works also with Ambrosio and Ota and Kuwada, and it is based on a relation between entropy and heat. I don't have time to develop this. This would be another whole seminar, but here you see also fundamental role of entropy. And I will conclude with a final example of entropy arises where you don't expect it. This is in theory that I contributed to develop with John Lott and Carl Theodor Sturm about a Ricci non-negative in synthetic way. What is Ricci curvature? Ricci curvature is one of the three most popular notions of curvature. At each point x, you are in a curved space like Riemannian manifold. At each x, Ricci is a quadratic form on the tangent space, which is obtained by taking the Riemann tensor and contracting it over two indices. Ricci curvature measures the rate of separation of geodesics in a given direction in the sense of volume. Curvature is always about separation of geodesics. Curvature negative is you separate faster. Curvature positive if you separate more slowly. And how much you separate, if you measure it in the sense of distance, you get sectional curvature. If it is in the sense of volume, you get the Ricci curvature. This is a classical interpretation of Ricci curvature in terms of distortion. Imagine you are here, and you're observing some light source, some star or some distant star or whatever. And the light rays go through geodesics, and you're observing them, and because you live in a curved space, you don't observe exactly what you would have in a Euclidean space. But this you don't know. And when you are here and try to reconstruct the source, you will overestimate the size of the source. So there is a positive distortion. The object appears to you larger than it is in real life. Because of positive curvature effects, the observer overestimates the surface of the light source. Distortion coefficients is a way to make sense of this very precisely with some limits and so on. And these distortion coefficients are always greater than 1 if and only Ricci curvature is non-negative. This is a classical interpretation of Ricci. Now, connection between optimal transport of probability measures and Ricci curvature was recently studied. Okay, I say recently, but this is already 5 years ago, let's say, or a bit more. Started with paper of Felix Otto and myself, 1999, very first occurrence of Ricci. And the theorem that has been obtained by these tools and was completely unexpected in geometric context is this. Okay, no, this is a theorem that was expected. Limit of manifolds with non-negative Ricci curvature is also of non-negative curvature. This looks like a very simple theorem. What was not expected is the proof. Why? First, why is this theorem interesting? Because the convergence is very, very weak. Measured Gromov-Hausdorff topology, roughly speaking, you just ensure the convergence of distance and volume. So it's a problem. You have convergence of manifolds converging, but you don't impose that the metric tensor converges in a smooth way. Just the distance and the volume. And because distance and volume is morally the meaning of Ricci curvature, you'd like to be able to pass to the limit with just this. And why I say this in this talk is that the key ingredient in the proof is the Boltzmann entropy. Why? And this will be the last slide. Let me call this the lazy gas experiment. And this is how you would explain Ricci curvature to Boltzmann. So you want an experiment to describe if you are a non-negative Ricci curvature or no. You have a gas in your space which has a certain density configuration. So at certain places it is high density, at some places low density. And you are his master, and you order the gas to arrive at another configuration after time equals 1 minute. So the gas will obey and will transport all its particles to arrive at some other configuration. And in the process, since the gas is lazy, he will choose a path that demands the least amount of effort, so that the total action, which is the integral of the kinetic energy, is minimum. And in between, you record at each moment of time the density profile of the gas and the entropy which is associated, the Boltzmann entropy, the amount of uncertainty contained microscopically in the gas. And then you plot as a function of time this entropy, and this should always be a concave curve of time. If it's always a concave curve of time, you live in a space of non-negative Ricci curvature, and there is an equivalence. So with this example, I will, so once again, we see here entropy arrives where we don't expect it. And thank you, Mr. Boltzmann, in a way. Okay?